Reinforcement learning is a branch of machine learning that is inspired by how humans learn. The actor or the policy takes an action and ends up in the new state of the environment. The actor repeats a new action based on the state, and the cycle repeats. The value or the critic continuously evaluates the reward from the environment and provides loss information to perform gradient descent. The advantage is formulated as the increase in reward that you would expect when you perform an action that deviates from the current policy pi. The loss function is an expectation of the log probability of a particular action and the advantage from performing that action. Rewards are very sparse or absent in real world. Life is not an Atari game. The authors model curiosity as an intrinsic reward signal for learning exploration. Children are very fast learners, and this is attributed to their curiosity. The authors model the error in predicting the consequences of the agent action as an intrinsic curiosity reward signal. The key highlight of this paper is that the running score is not used as a reward to learn to play the game. The original paper explores Wisdom and Super Mario Bros. Environments for evaluation. In my implementation, I will be using the OpenAI Gym, Cartpole, and Mountain Car environments. To model curiosity, we need three additional networks. The feature network represents the environment as phi of st, which is a lower order representation of the environment. The forward network predicts the next state given a particular action. The difference between the predicted next state and the actual next state is formulated as our intrinsic reward. This is the loss function that we aim to maximize. The key takeaway here is that if the agent fails to predict its action correctly, we give a high curiosity reward signal. This signal enables the agent to explore much more effectively. In the carpool environment, a pole is attached by an actuated joint to the cart, which moves along a frictionless track. A reward of +1 is given every time the pole remains upright, and the episode ends when the pole is more than 15 degrees from the vertical. On the right side, we see the average reward trend and the corresponding agent in action. Training with vanilla A to C without curiosity, it results in a very slow convergence and the agent is not very stable. Training with extrinsic reward signal and intrinsic reward signal gives very high rewards to start with. The resulting agent is very stable. Finally, the agent without an extrinsic reward still learns to balance the cart. This slide describes the internal workings of a curious agent. As the reward signal begins to saturate, the agent tries to explore new states of the environment. This exploration causes the agent to sometimes go beyond 15 degrees and fail. Even though this results in a lower average reward, a high intrinsic curiosity reward signal is received and the agent learns not to topple over in the future. For conclusion and future work, we have demonstrated the ability of a curious agent to explore the environment better and consequently result in a robust agent. The original paper describes that the ICM method learns well even with 40% white noise. The ICM agent learns to ignore the white noise and concentrates on the area that matters. We plan to run experiments with noisy states in the environment and evaluate the benefits of feature extractor. The mountain car environment that we trained failed to effectively converge. We want to explore the reward shaping to model gravity as well as explore other policy gradient algorithms. Thank you.